Hey, it's Mr. Shrum, and welcome back to our physical science tutorial walkthrough lessons. Last time we looked at the periodic table, and in this lesson, we're going to look at trends within the table itself. And this will give you a better understanding of how to understand the table, how to use it, and the little tricks and tips I have for you will help you with that. We're going to identify and then compare the trends to one another. Here's the contents. And for the introduction, all right, so imagine that you're experimenting with a set of metallic elements to prepare oxides from each of them. You're not sure which of these elements will get you the desired result. How could you predict how a particular element will react with oxygen, in this case, to make an oxide? You really don't want to start mixing chemicals blindly to see what happens. That's always a bad idea. You have to be careful and consider what can happen when certain things mix. So to predict the behavior of of elements, you can simply refer to the periodic table. You know that elements with similar characteristics form groups within the periodic table. If you look closer at the periodic table, you'll notice a trend in these characteristics. Depending on the location of the elements in the table, and in this lesson, you'll explore trends in elements related to atomic radius, ionic radius, ionization energy, and electronegativity. And the first one we're going to look at is atomic radius. So this picture shows you what atomic radius means and the distance between nuclei. And this is a little nucleus in between the atoms, okay? An atomic radius is the distance from the nucleus to the outermost electron of the atom. Since this distance is very small, it's measured in angstroms, or 10 to the negative 14th power of a meter. Very, very small. Determining the atomic radii of an element is difficult because atoms don't have a fixed size. Electrons inhabit cloud-like orbitals that tell us the probability of where the electrons might be located. Not definitive though, might be. But the orbitals don't indicate fixed locations or distances for the electrons. We can, however, calculate the atomic radius by measuring the distance between the two nuclei of a diatomic molecule and then dividing that distance by 2. For instance, the distance between the nuclei in a diatomic bromine molecule is 238 picometers. Dividing this value by 2 gives us an atomic radius of 1.19 angstroms for each bromine atom. So if you find 2 atoms together, you can measure between the nuclei and divide by 2, since it's hard to measure between the outermost electron and a nuclei, or a nucleus. This activity tells you to open the periodic table tool that we've learned before, or we looked at before, to explore patterns in atomic radius for elements. So we'll click that, click the Trends tab up here. So we've got that. And then from the trend selection near the top, we're going to pick atomic radius. Bam. Okay. So notice the atomic radius. How it's increasing within the group as you move vertically down. in most cases. So that's why they call it trends. It's not always the case. But look at the graphical display for the group 1 elements. What pattern do you observe about atomic radii? Radii is plural for radius. You don't say radiuses, you say radii. And as you move from hydrogen at the top to the table, to the bottom of francium, sorry, what happens? Do you see a pattern? So we have 1.1, 1.82, 2.27, 2.75, 3.03, 3.43, 3.48. So what's the pattern we see here? As you move from hydrogen to francium, the atomic radii of the elements generally increase. So as you move down, group 1, the radii increases generally. In addition to looking at the graphical display, select each element to see its quick facts display and record its atomic radius in the table below. That is the end result after doing that. Look at the graphical display for the period 3 elements. What do you observe regarding atomic radii as you move from lithium on the left to neon on the right? So we're going to look at the 3rd period. This is 1st, 2nd, 3rd period. This is period 3. But it must mean period 2. Well, anyway, we're going to start with lithium and move our way to neon. Lithium 1.82, beryllium 1.53. So we were at 1.82. It went down 1.53. Then back up 1.92, 1.7, 1.55, 1.52, 1.47, 1.54. So as you move from lithium to neon, the atomic radii go up and down, but generally trend smaller as you go toward the right end. So you have bits where it jumps up and down, but we started out at 1.82 and we ended at 1.54. So it generally went down. So going down a group, the atomic radii goes up, moving down the period. Generally, the atomic radii goes down, lowers. Now it wants you to record the atomic radius for these elements in that period. And this is the end result of that. What are your conclusions about the trends of the radii, atomic radii, in the periodic table? Tie your conclusion to your understanding of atomic structure. So, as you move down in a group, the number of shells in an atom increases. The electrons in the outer shell are farther away from the nucleus, so the atomic radius increases as you move down. As you move from left to right, the elements gain electrons, but the number of shells remains constant. The extra electrons experience a stronger attraction towards the nucleus, and that reduces the size of the atom. So the atomic radius generally decreases as you move from left to right in a period. The variation in this decrease is due to the complexity of the build for the various orbitals within the shell. In the atomic radius activity, you saw how the atomic radii of elements increase as you move down from hydrogen to lithium, then to sodium, and then potassium. This trend indicates that the atomic radius generally increases as we move from the top to the bottom in a group. As you move down a group, electrons are added to new energy levels. Within a group, the sizes of these energy levels increase and the electrons occupying them move farther and farther away from the nucleus. This movement results in an increase in the size of an atom. The effect is similar to piling on layers of clothing for a football game, which you could say increases your personal radius. Now that you know what happens as you move down a group, let's look at what happens to the atomic radii when you move from sodium to silicon. The atomic radius decreases when you move from left to right, for the most part. As you move from left to right, the atoms gain an extra proton and an extra electron. The added electrons either go into the valence shell or into sublevels below the valence shell. The added protons increase the central positive charge, pulling the valence electron shell closer to the nucleus. That makes the atomic radius smaller. So atoms generally become larger as you move down a group and smaller as you move from left to right in a period. You'll notice that the largest atoms are located in the lower left of the periodic table, with the smallest atoms, while the smallest atoms are located in the upper right. So smallest in the upper right, largest in the lower left. Largest, smallest. All right. And I'll stop there for now. And when I come back, we'll start looking at ionic radius and see how that differs. But until next time, see you later. Have a good one. Bye-bye.